Okay, working on the last problem in chapter 12 that we worked on together as a sample problem, we're predicting the type of intermolecular forces. And then again, we can use those intermolecular forces to predict which one has the higher boiling point. And we learned about many physical properties in this chapter, from boiling point to melting point, and we also learned about viscosity and surface tension today. And so anytime you have higher intermolecular forces, that's going to create a higher boiling point, a higher melting point, higher viscosity, and greater surface tension. So intermolecular forces are really important to consider. And just kind of as a start to this problem, let's kind of remember the hierarchy of intermolecular forces that we have. Kind of the weakest on our chart are London dispersion forces. And all molecules are always going to have London dispersion forces. And remember, those are interactions essentially of surface areas. So polar and nonpolar molecules will all have London dispersion forces. Then the rest of the list kind of goes like this. We have dipole, induced dipole, and that's going to be between a polar molecule and a nonpolar molecule. Because remember, nonpolar molecules don't have a dipole, but if they're next to something that's polar, a dipole can be induced. Next on our list is dipole-dipole, and that's going to again be between two polar molecules. So it's really important that we be able to look at molecules and ask the question about, are you polar or not? Just to review for a second, if you want to ask if a molecule is polar, you first have to ask if there's polar bonds. Asking if there's polar bonds means asking, are two different atoms connected to one another that are not carbon and hydrogen? If two atoms are connected and they're the same bond or the same atom, that is not generally a nonpolar bond. If two atoms are connected and they're different, but they're not carbon and hydrogen, the electronegativity difference is such that it will be a polar bond. But just because a molecule has polar bonds doesn't mean it's a polar molecule. Remember, what this really means is there's a tug of war going on, particularly in small molecules. So if two bonds are pulling in opposite directions such that they cancel out, then that molecule will end up being nonpolar. Go back and review that from our slides in chapter 12 if what I've said there is kind of confusing. All right, so after London dispersion forces, we've got dipole-induced dipole, dipole-dipole between two polar molecules, a special kind of dipole-dipole interaction, which is hydrogen bonding, and the last problem reviewed what you need to have in order to have hydrogen bonding. Then we have ion dipole, and then lastly we have ion-ion interactions, which this is an ionic compound. What we can see here as we go through this hierarchy is we basically have a molecule or two molecules that are completely nonpolar, and as we move through this, what we're changing is the magnitude and the permanence of a charge on each of these individual molecules. The magnitude and the permanence on ions is very large, whereas we're down here, the magnitude but the permanence are very small. Okay, so let's just go through this problem here. We need to compare two different substances, and whoever has the greater number of intermolecular interactions is going to have the higher boiling point. So for this first problem, we've got magnesium chloride, and then we've got PCl3. Well, hopefully you can recognize by looking at magnesium chloride, we made this substance by taking a molecule or an atom from the left side and the right side of the periodic table. This makes it an ionic compound. That means we're going to have ion-ion interactions. That's the strongest kind of intermolecular force we can have. It's not truly an intermolecular force because these aren't molecules, they're ions. This is a very strong interaction. Let's look at PCl3. Again, phosphorus and chlorine both come from the nonmetal side of the periodic table, so this tells us that we have a covalent compound. If we draw what a Lewis structure would look like for this compound, this is what it's going to look like. Okay, we have tetrahedral geometry, we have polar bonds, but again the shape of this is such that we're not going to have these dipoles cancel out. So this is a polar molecule. So you've got again dipoles here, this is a polar molecule. If we were to draw the dipoles in, you could draw them like this. All right. Every molecule will always have London dispersion forces. If we have a polar molecule, we're going to have dipole-dipole interactions. This molecule is not, however, capable of hydrogen bonding. look back at sample problem 12.3 to review hydrogen bonding, we don't have any hydrogen atoms that are attached to nitrogen, oxygen, or fluorine. So in this case, all we have are London dispersion forces and dipole-dipole interactions. We've gone all the way up to the highest part of our hierarchy here. So in this case, magnesium chloride is going to have the highest boiling point. And just as reference, the boiling point, and I know you don't normally think of boiling as salt, but the boiling point for magnesium chloride is 1,412 degrees. For phosphorus trichloride, the boiling point is 76 degrees. Wouldn't expect you to know those, but again, just confirmation with some real numbers that the greater intermolecular forces will translate into a greater boiling point. Okay, let's take our next problem here. We've got CH3NH2 or CH3F. I'm going to start drawing my CH3 molecules like this, rather than on the previous problem where I drew out all the hydrogens, because there's really not any functional chemistry that we're going to be thinking about with that. And there's really not any contribution significantly to our intermolecular forces, because this is a nonpolar part of this molecule. However, this part is important, because what we can see here is we have a molecule capable of participating in hydrogen bonding with, and when I say itself, another molecule of this same compound sitting next to it. So again, if we go up our list, we've got London forces, we have a polar molecule because we have polar bonds here. So we're going to have dipole-dipole interactions, and we also have the ability for hydrogen bonding. So we've moved all the way up the chart here with hydrogen bonding. If we look at our next molecule here, and again, if I draw this out, because this one tends to confuse students because they see hydrogen and they see fluorine in this. And even how this is set up, it looks like the hydrogen and the fluorine are next to one another, like they could be bonded to one another. But what we really have here is we have the carbon as the central atom, bonded to 3 hydrogens, and then the carbon is bonded to the fluorine. There's no hydrogens bonded to the fluorine, so there's no possibility for hydrogen bonding. This is, however, a polar molecule. So it has London forces and it has dipole-dipole interactions. But in the absence of the ability to do any hydrogen bonding, this is not going to have as strong intermolecular forces as we see with problem B. So we would predict that this guy would have greater intermolecular forces and we would have a higher boiling point. And in that case, indeed that is the case. And to put down some real numbers here, the boiling point of this substance is minus 6.3 degrees Celsius, and the boiling point over here is minus 78.4 degrees. Make sure to notice that that's a minus there, so this boils at a much lower temperature, and that's again because it has fewer intermolecular forces. Our next problem here, we've got methanol versus ethanol. Now again, with most of these problems, what I'm going to be giving you is kind of an apples to apples or oranges to oranges comparison. Both of these first two problems had molecules that differed in the kinds of intermolecular forces that they had. So it was easy to say the molecule with the greater number of possible intermolecular forces is going to have the greater boiling point. If we run through that same checklist for these two substances, and as we'll learn in a couple of chapters, having this OH group makes these compounds alcohols. They both have the same number of intermolecular forces. They've got London dispersion forces, and they both have the ability to hydrogen bond. So we need to ask the question, what's different with these two molecules? And if we try to ask what's different, the only thing that we can see that's truly different is the size. So when you have the same intermolecular forces, what you really are probably going to need to look at is the size and the shape of these molecules. And in this case, larger molecules or molecules that have greater surface area that can interact are going to have greater intermolecular forces. So we would predict that there would be greater intermolecular forces with ethanol, and that is indeed the case. You might remember from the earlier problem that we did on vapor pressure with ethanol that the boiling point of ethanol is about 78 degrees. The boiling point for methanol isn't substantially different, but it is lower at 64.7 degrees. The last problem also builds on this difference, not in the kind of intermolecular forces or the numbers of intermolecular forces in terms of choosing different things from this hierarchy, but it looks at differences in size and or shape. So again, we've got hexane, and rather than redrawing these molecules, I'm just going to work on this problem from up here. We've got hexane, or a molecule called 2,2-dimethylbutane. And as we'll learn about in chapter 15, these molecules are isomers of one another. They both have 6 carbons and the same number of hydrogen atoms, but what's different is how those atoms are arranged. So they're isomers of one another. Iso meaning same, mer meaning part. So they have the same parts, but they're just arranged in a different shape. These are both what we call hydrocarbons. They only have carbon and hydrogen atoms. So they don't even get to go up into this area of our hierarchy because having only carbon and hydrogen bonds or carbon and carbon bonds, these are nonpolar molecules. So the only thing they have are London dispersion forces. So if we're going to ask what's different about these molecules, what we're going to look at is the fact that they have different shapes. Hexane is very cylindrical, has all of the carbon atoms connected in a single chain, whereas 2,2-dimethylbutane is much more spherical in nature. 4 carbon atoms are connected together, and then we have 2 branch points. So if we think about the amount of surface area that we can have when 2 spheres touch versus when 2 cylinders touch, we can have a lot more surface area when 2 cylinders touch. So we would predict that hexane is going to have a higher boiling point versus 2,2-dimethylbutane. And indeed, if we put some real numbers with this, we can see that hexane has a boiling point of 69 degrees C, whereas 2,2-dimethylbutane has a boiling point of 49.7 degrees.